Okay, let's first review what we learned last week. Last week we completed a discussion of amplitude modulation, right? So we discussed a double sideband probably 2 weeks ago. And based on that, based on double sideband, based on mathematics, we eventually come to the single sideband. And in single sideband, there is an upper single sideband, and also there's a lower single sideband, right? So if you look at the double sideband, in fact, the double sideband is addition of upper sideband and single sideband, lower sideband, right? Because the upper sideband is outer band, and lower sideband is inner one, right? So somehow you can say that when you add the upper side and lower side, it's going to be double sideband. So based on all the mathematics, we know that, or maybe you can put it another way, single sideband, upper single sideband, you can say that it is a double sideband minus some other things, right? In this case, this means the second part is something unique for single sideband. And when you look at the upper single sideband equation, the first term is the same as a double sideband. That minus, you have some other term, right? So in order to get that, we need to know the Hilbert transform, right? Remember Hilbert transform? So based on the Hilbert transform, as an example, when you put the cosine into a Hilbert transform, you are going to get sine. Same way, you have your own message signal, and your message is mt. And put the mt into Hilbert transform, now you're going to get m hat t, which looks like this. When you have a triangle mt, right? Triangle mf, to transfer frequency response, then you're going to get this kind of frequency response after you go through the Hilbert transform. Now what you need to do is you want to multiply sine into here, right? Then you're going to get this signal, and this was original double sideband. And when you do this one minus this, then you're going to get upper sideband, and this plus that, you're going to get lower sideband, right? So that's the case of lower sideband. That's the whole message of the single sideband. Okay. For the receiver of single sideband, one thing that you want to remember is the receiver structure is the same as double sideband. Okay. Single sideband does not have a special receiver. This one, single sideband, requires a special transmitter. Right? In the transmitter, you need to do Hilbert transform. You need to do some other, like a multiplying sign after Hilbert transform, and all these things, right? Everything should be done at the transmitter. Receiver, you can do the same thing. You can do the same way as the double sideband. And this picture shows you the Costas receiver, right? Or we can say phase discrimination method. I'm sorry, this is a transmitter side. So this looks almost the same as a Costas receiver, but this is how you make the single sideband. And this one is also another thing that we discussed. What you can see from this picture is mixer. Okay? Remember the name mixer. Mixer is actual hardware. And that hardware mixing two different frequencies. The input, we have two inputs, right? Each input is a different frequency. And this mixer is a kind of mixing two different frequencies to create adding these two different frequencies or subtracting. So it's like F1 from one input, and let's say F2 from the second input, then the output can be F1 plus F2 or F1 minus F2. Okay? You can get either one. So you're going to get both frequencies, but eventually when you put the band pass filter to one of them, and then you'll get the other one. Okay? That's the output, typical output of the mixer. I think I remember that I have this question in the midterm, probably last year, right? I think so. So this is important. So maybe I can give you like one frequency, let's say 1 kilohertz, and maybe 2 kilohertz. And how do you create some other frequency? Then what you need to do is you need to do mixing. By mixing, you can create the new frequency. Okay, so that's one of the things. And we also discussed the vestigial sideband, right? Relatively, I think this is not that important, but the message here in the VSB is that this is your original message, MF, right? By multiplying cosine into time domain, now you're going to get DSB signal. That's a DSB, double sideband. From this double sideband, now you want to put the shape filter, like a filter. This is filter, like bandpass filter, but this is a very specially designed shape. Okay, this has a very special shape. So by putting this shape filter, put this one as an input to the filter, now you're going to get this output, and that's the output of your VSB. So you are transmitting this signal over the air. By the way, this is a frequency domain, right? Right? So this is the frequency response of the transmitted signal over the air. Okay, so that's a VSB. And the idea is that at the receiver, what you need to do is you want to multiply the cosine. When you multiply the cosine here, this one can go to there in the 2FC, and also this one goes to the baseband. Same way, this one also goes to the baseband and also minus 2FC, right? And by putting bandpass filter, minus 2FC component and 2FC component will be gone. Those are high frequency component. Only the DC part, like a baseband, will be recovered. But that, after you multiply cosine at the receiver, this one and this one added together, and you're going to perfectly recover the original message. Okay? That's the intention of vestigial sideband. Okay, now what we're going to start from today is angle modulation. Okay, so far we discussed the amplitude modulation, but now we're going to talk about angle modulation. Okay, we're going to talk about the detail, what is angle and what's the difference between the amplitude and angle modulations and things like that. First of all, what is the angle? Angle is this is angle, by the way. You see that this is kind of carrier, right? But we say that just the ST, like a generic sinusoidal wave. But when you look at this one as a carrier, for example, this one is angle. Okay, whatever inside the cosine, that's the angle. So what this angle modulation is, you're going to put the message into the angle. What was the amplitude modulation? You want to put the message into the amplitude of the carrier. Now, in the angle modulation, we're going to put the message into the angle. Okay, that's the idea. Generally, angle modulation is a nonlinear process, okay, which means a little bit complex. Okay, we're going to talk about the details later. And not only that, what this says is that your transmission bandwidth of your angle modulation sometimes is increasing. Okay, your bandwidth changes. That's what that means. Sometimes, ideally, in theory, your bandwidth requires a infinite sometimes. Okay, again, this is covered later. The next thing here, it says the amplitude of a carrier wave maintained constant. Why is that? Because your message is not in the amplitude. Your message goes to angle. So amplitude is same as before, right? Because amplitude, we didn't touch anything. So amplitude remains constant because we didn't change anything. What we're going to do is we're going to put the message into the angle. Okay? So in general, your amplitude of your carrier is the same, is constant. Earlier in the amplitude modulation, now you put the message into the amplitude, right? So since your message goes to amplitude, of course amplitude changes depending on your message. But now in this angle modulation, your message goes to angle. And the amplitude is still same, remains the same. So the amplitude is not change, and not going to change, and it's constant. And because of that, the big advantage of angle modulation is it is a little bit strong for the noisy environment. When you have a noise, right? Let's say you have a noise. So far, we assume that there's no noise. We transmit ST, and your receiver receives same exactly ST, right? We never considered noise. But later, maybe after midterm, later in this semester, we're going to talk about noise. When you have a noise, right, you transmit ST, but ST plus noise is received. Okay? When you receive, you have a noise. But what is a noise? Noise actually changes your amplitude, right? Let's say you transmit it, let's think about voltage. You transmit 5 volts from the transmitter. But when you receive, you are not going to receive exactly 5. Because of the noise, sometimes you get 4.7, sometimes like 5.2, something like this, right? Because of the noise. So noise typically goes into the amplitude. Your amplitude fluctuates because there's a noise. So amplitude modulation, the previous amplitude modulation, when you have a noise, your signal changes because of the noise. But in this angle modulation, it doesn't matter. Why? Because your message is not in amplitude. Amplitude maybe have a noise, it fluctuates, but doesn't matter, right? Because noise does not affect in general. Okay, we'll talk about those details later. There are 2 types of angle modulation. One is phase modulation. The other is frequency modulation. Okay? Again, we're going to discuss that in a minute. So, all of the analog communication or analog modulation, we always start from this simple sinusoidal signal. Okay? We always start from this. And based on that, when we talk about amplitude modulation, what was that? We're going to put the message into amplitude side. Okay? That's the amplitude modulation. Now we are talking about angle modulation. So what we need to do is now we want to put the message into angle. Okay? That's the idea. But there are 2 ways to do it. One is phase modulation, or we can call it as a PM. Second is frequency modulation. It's FM. Okay? That's how we call it. What is a PM modulation? To understand that, we need to know what is a phase. So when you look at the angle here, theta IT, typically this angle has this kind of thing and also this, right? So we have 2 terms. The first term is like a 2 pi FCT, and FC is a frequency of that particular cosine, right? 2 pi FCT plus some other things. That is a phase, right? Remember that we discussed the double sideband? When you have a phase mismatch, we discussed the phase mismatch, right? That phase was a phi. That's a phase. So we typically have a 2 pi FCT plus phi in here, right? So that's what we have. For example, right? Think about the carrier. Always carrier may have its own amplitude, carrier amplitude, cosine 2 pi FCT plus phi. We always start from here, right? And if you put the message into here, that's amplitude modulation. When you put the message into frequency part, that's going to be frequency modulation. When you put the message into phase, that's going to be phase modulation. That's the difference, right? And frequency modulation and also phase modulation, that's still part of the angle. So this amplitude, constant, because we don't change, right? This is still constant because we put the message into angle. Now in the phase modulation, we're going to put the message into angle, message into phase. This is phase. And we're going to put the message into here because this is phase modulation. So that's this one, right? This is your message. And earlier in here in the equation, this is a phi. Okay? In this phi, we're going to put the message into here in the phi. So this is same as phi. Right? So in the PM, phase modulation, we want to put the message into here. So how to do that is put the message here, and we want to multiply some gain, Kp. That's our message. That's how you put the message into the phase. Okay? So this simply, now you look at ST here, right? This looks a little bit complicated, but it's not complicated. AC cosine, and we have 2 pi FCT plus phi earlier, but now we put the message into the phase, so we want to have a Kp which is just constant value, and empty. So that's where your message goes, right? This is phase. So this is what you transmit over the air if you use a PM. Okay, simple. So your message goes to phase part. Now in the frequency modulation, your message now goes to frequency. So your frequency is Fi here, and this is, let's say, this is your frequency, okay, after you do modulation. But this Fc is your original modulation. This is your original modulation, right? And now, in addition to your original modulation, depending on your message, your frequency, whole frequency is now changing. That's the frequency modulation. Okay, so let me put it this way. And when you look at the frequency modulation, typically you will see integration like this. So this one is, in conclusion, this one is your frequency modulated signal. After you do frequency modulation, you're going to transmit this signal. So when you look at here, the first part is a 2 pi FCT, same. And the second part, you have an integration like this, right? This one looks a little bit difficult, looks a little bit complex, right? So let me tell you, let me put it in another way. Maybe this is a little bit easier to understand. So as I said, in FM, in frequency modulation, what you want to do is your message, now you want to put it into the frequency. So that's your frequency modulation, right? You want to put your message into the frequency part. Frequency. So how to do that is after you do the frequency modulation, something like this. This is not exactly same as that, but I'm just giving you an idea. Okay? What this means is now, after you do the frequency modulation, in the original carrier, you only have FC. But after you do the frequency modulation, now your frequency is changing, depending on your message. Okay, that's the frequency modulation. So here's the idea. Let's say you have amplitude modulation. In the amplitude modulation, let's say you have a message. This is your message. Then depending on your message, and this is your carrier, CT, right? This is MT. This is your original message. This is your carrier. And in the amplitude modulation, your carrier times your message will give you something like this, right? Your ST transmit signal has the different amplitude depending on your message, right? Because your message goes to the amplitude. But in this frequency modulation, amplitude is not changing, but depending on your message, your frequency is changing. In the earlier amplitude modulation, frequency is always the same. Frequency never changes, right? Your message will change your amplitude, but frequency is same. But in this frequency modulation, now the frequency changes. Frequency, okay? Your frequency changes. Now the question. Which one has a higher frequency? This is a higher frequency, right? Of course, right? So now, when you look at the frequency modulation, now frequency is changing. Frequency is changing, right? So depending on your message, frequency changes. I'll show you later. And by the way, when you do this, right? Think about this way. When you do this, let me write it again. AC cosine. Now we can think about two terms. 2 pi FCT plus, I missed one thing. Yeah, that's right. 2 pi, let me put here as a kf, just constant value, then kf mt times t plus phi. So this one and this one same, right? I just expand these two terms. Now we have these two terms, right? Three terms. Actually phase, let's ignore the phase because this is a frequency modulation. So now we can think about two terms. And the reason that we have two terms is because that your frequency is not constant anymore. Your frequency is changing depending on your message, right? This frequency part is changing. Now we know this one, 2 pi fct. We always see that. What is this term? The second term. We have a 2 pi kf. That's constant, so that's okay. But what is this one? mt times t. Let's take a look at this one in mathematics. Let's say this is time domain, and we want to look at our message mt. And let's say our message looks like this. Here's a 0. What this means is if you pick a t here somewhere, then this mt is this one, mt. Right here, right? That's your, this mt means here. And this t means there. So when you multiply mt times t, that means this times this. What that means is this area. That's what they mean, right? So if you put the mt small like this, then it's going to be this area. How do you get this area? By doing integration. That's how you get this area, right? This integration gives you the area under this function, right? So this somehow, this one is the same as this. You see that? You see the integration? So it's this equation looks a little bit complex because you have integration, but the meaning is, original meaning of that is this one. Your frequency is not constant anymore. Your frequency is now changing depending on your message. Sometimes, depending on your message, sometimes the frequency goes to higher, sometimes lower. Okay, it keeps changing. And when you rewrite this one or mathematics, then you can write it this way. Okay, that's the frequency modulation. So comparing the phase modulation and frequency modulation, now you can say that instantaneous phase, we cannot write it this way or this way. So this is what we just looked at in the previous slide as a phase modulation. Here's a phase. So in the phase modulation, you can put your message into the phase. So it looks a little bit easier. In the frequency modulation, your message actually goes to frequency. This one looks like your message goes to phase, right? It looks like, right? Because the message is in here, second term, right? But it is not. Okay, that's what I'm saying here. Your message does not go to the phase. Your message goes to frequency because this is frequency modulation, right? But when you rewrite into two different terms, eventually it looks like this. That's what they mean, right? This one is a phase modulation, so message goes to phase. That's correct. But this one, frequency modulation, so your message goes to frequency. But when you rewrite it into this way, now you're going to see it this way. That's what they mean. Okay? So this is our frequency modulation. Let's visualize all these things, what happened. Let's say this is a carrier signal, like a CT, right? This is your carrier, and our frequency of carrier is a carrier frequency, FC. So this is your carrier. Now we have a message. This is our message in time domain. Okay? Just simply sinusoidal in this case. Let's put this message and multiply with the carrier. Then you're going to get amplitude modulation. In this amplitude modulation, based on your message, your carrier changes its own envelope, right? Your envelope of the carrier changes depending on your message. So we know that, right? We already know that. But when you look at here, the frequency never changes. How do you know? How to know is that you are trying to find that zero crossing points, like here, right? Positive to negative, negative to positive. Here are all the zero crossing points. These zero crossing points is all regular, like a regular, because in the original carrier, it's always like that, right? This single carrier, like a one frequency, carrier frequency. So wavelength is the same. So you should have a same wavelength. So the frequency does not change. Only amplitude changes. Now let's look at the phase modulation and frequency modulation. One thing that you can notice is that amplitude is always constant. Amplitude does not change, right? For both of them, because you're not going to touch any amplitude. The only change is that, let's look at this first. In frequency modulation, you see that the frequency is changing. Here, high frequency, probably low frequency, and again high frequency, right? So something like, depending on your message, it's like a high, there is always a fundamental frequency. Fundamental frequency is FC. So your FC is the original frequency. And when your message goes up, your carrier frequency goes higher, like FC plus alpha, and go back to FC and FC minus alpha, something like that. So it's like your frequency is high, down, low, higher, lower, something like this, right? Your frequency is changing. So that's why you see this, right? This is like here you see that the frequency here is FC plus alpha. It's a higher frequency than FC. Here it's a lower frequency than FC. You can easily compare this, right? Here you can see lower frequency. Here it's a higher frequency. So the frequency goes higher, lower, depending on your message. That's a frequency modulation. In the phase modulation, you can see it looks pretty similar, right? But in phase modulation, it looks like a frequency is changing, but in fact it is a phase what is changed. So here's what happened. Look at here. Whenever you have, okay, let's look at the phase. Phase here is 0, right? Phase is changing over here. That's 90 degree, 180 degree, right? And minus 90 or 0, something like this, right? The phase changes that way. Typically, when you look at phase is from minus phi to phi. We typically look at the range of the phase as a minus phi to phi, not 0 to 2 phi. Okay, phase is typically like minus 180 all the way to positive 180. Okay, that's the change. That's the range of your phase. So here the phase changes like from 0, keep changing, keep going up until 180 degree, and again going down to 0. Something like this, right? So that's what you see here. You have some phase, and now your phase is changing, and again come back to the phase, 0. Something like this, right? That's what you can see. But when you have this constantly changing phase, it appears as the frequency is changing. So somehow you can say that the phase modulation and frequency modulation, it's very close, right? Very closely related. Even though you see the phase modulation, sometimes it looks like a frequency is changing. And when you look at the frequency modulation, sometimes it looks like phase modulation. It's very close, very close. Okay? So we're going to look at it. We're going to look at it a little bit different in the next slide. This is another example. This is a digital example, so it's probably easier to understand. Let's see, the first here is a carrier frequency. Okay, this first is a carrier. And the second, it's like a on-off. This is an on-off signal. That's your message. Now my message is like a digital, 0, 1, 0, 0, 0, 1, something like this, right? This is my message. In the previous example, this was my message, right? It's an analog message. But in this example, my message is like a digital, 0, 1, 0, 0, 1. Now, when you do the amplitude modulation, okay, what happens is depending on your message, your amplitude is changed. For example, like this. When you get some 0, for example, you have this small amplitude. When you have a 1, maybe you have a higher amplitude. So your amplitude changes depending on your message. But still the frequency is same. Okay, frequency is not affected. This one, this D, this one shows your frequency modulation. When your input, your message is a 0, maybe you have a same frequency as a carrier, but when your message is 1, now you have a higher frequency. And come back to original frequency, and again higher frequency. So since we have two different data, right? It's like either 0 or 1. It's binary. Your message is 1 or 0. So how many different frequencies do you need? 2 only, because you have only 2 different input, right? It's going to be 0 or 1. Just simply 0 or 1. So 0, this frequency, 1, that frequency. That's the frequency modulation. Like a 0, that frequency, 1, that frequency. That's what you see here, right? Whenever you have a 0, you have this frequency. Whenever you have 1, you have a higher frequency. That's simply frequency modulation. The last thing here is a PM, phase modulation. And how to do that in phase modulation is whenever you have a 0, whenever you have original message 0, phase 0. And when you have a message 1, phase 180 degree. When you add the phase 180 degree, what does that mean? Cosine becomes minus cosine because you add the phase 180 degree. It's like a phase rotation, like a sign change, right? Plus becomes minus, minus becomes plus. So that's what you see here. You see suddenly here, you see phase change, right? It's like a going up and suddenly going down. It's like a reverse. Here, same, right? It's suddenly reverse. Same here, reverse. But looking here, the frequency same, because this is a PM, right? PM, phase modulation. So what is changing is phase. Here, frequency modulation. So what is changing is frequency. This is phase modulation. So you are changing phase depending on your message. This is another example, pretty much the same example, but another way of doing it. So this one again, our message, original message is digital, 010010. You see here, right? This is my message. This is my message signal in time domain. When you put the amplitude modulation, in this case, what I'm trying to do is whenever you have a message 0, I'm not doing anything. And whenever I transmit information 1, I transmit carrier. So this message 0101 is now multiplied with carrier. So 0 times carrier, nothing. 1 times carrier, you get carrier. Okay? Something like that, right? That's one way of amplitude modulation. Amplitude changes, right? Amplitude disappear. Now you have something. You have nothing, something, nothing, something. Right? So again, this is amplitude modulation because amplitude changes. Here shows you a frequency modulation. Right? You see that frequency here, whenever you have a 0, you have this frequency. Whenever you see 1, you have a higher frequency. So frequency change, right? Depending on your 0, 1. So this is a frequency modulation. And this one again, phase modulation. You see that every time 0, 1 or 1, 0 transition happen, you see the phase suddenly changes. Phase suddenly changes, right? Suddenly. So that's the PM signal, phase modulation. Okay. So these two are what we are learning now: frequency modulation and phase modulation. Here are properties of angle modulation. Okay. There are many properties. Let's briefly discuss one by one. First of all, in angle modulation, the transmit power is constant. Why? Because amplitude is constant, right? your amplitude is constant, so therefore your power, transmitting power is constant. This is actually a good one, very good, right? In the amplitude modulation, earlier amplitude modulation, depending on your message, your transmitting power changes, right? Because your amplitude changes, so power changes. But in this angle modulation, the angle amplitude is not going to change. Your information is in the frequency or phase. So therefore, your transmit power is going to be constant. So that's a very good one. And second thing, nonlinearity of a modulation process. This is not good, right? This is a nonlinear process, which means the process is a little bit complex. And also, because of nonlinearity, your hardware looks a little bit complex. But anyway, we'll talk about that a little bit later. This is not a good one. Property 3, irregularity of zero crossings. What that means is your frequency may be changing. So what was a zero crossing? From positive to negative, negative to positive. So if the zero crossing is regular, that means your frequency is constant. But in this case, it's irregular. So sometimes zero crossing is very often because of high frequency, or sometimes very slow. Okay, so that's what they mean. Your frequency basically changes. Yeah, that's what it is. And property 4, visualization difficulty. What that means is when you look at, let's say, FM modulation or PM modulation. Let's take a look at the PM modulation. From this PM modulation, we don't know what is the message inside the signal, right? Visually, you cannot find out what is the message. When you look at the amplitude modulation, it's very clear. Even visually, it's very clear what is the message. We can easily find out, oh, here's a 0, here's 1, 0, 0, 1. We can easily see it, right, visually. But in frequency and PM, typically that's very difficult. So it's like a visualization difficulty of your message in the transmitted waveform. Number 5, much later, maybe next week, we're going to look at some of these things. But in property 5, a trade-off of increase the transmission bandwidth for the improvement of noise performance. What is a trade-off? What the trade-off means? Trade-off in general, trade-off means you're going to lose something, you're going to get something, some other things, right? You can sometimes lose this one, then you are going to get another one. That's a trade-off, right? That's trade-off. So what this angle modulation do is you are doing trade-off by increase the transmission bandwidth. Increase the transmission bandwidth, is this good or bad? Transmission bandwidth is increased, good or bad? It's bad, right? Why? Remember the single sideband. What was the reason that we want to do single sideband? Double sideband is simpler. Then why do you want a single sideband? Because we want to reduce the transmission bandwidth into half, right? Single sideband use only half of the bandwidth. That's why. It's a complex, but transmission bandwidth becomes half of that, half of the DSB. So that's why we use a single sideband. So transmission bandwidth, we want to make it smaller if possible. But in this angle modulation, typically you need to have increased the transmission bandwidth. So that's bad, right? Because transmission bandwidth is increased, that is a bad thing. However, since we are talking about trade-off, you're gonna lose something, then you're gonna get another one, right? What do you get? This is what you're getting. This is a good one. Improve the noise performance. What that means is when you have a noise, okay, amplitude modulation, you're going to get a very noisy signal, and it's very difficult to recover your message. But in FM, noise doesn't really matter. It doesn't really matter. Noise does not affect much. Even though you have a noise, still you get a very good performance. So that's what they mean. So that's a good thing, right? you have immunity of noise, right? So that's what that means. So that's a good one. This is a bad one, but this is a good one. So you're kind of doing trade-off. So that is possible for this angle modulation. Amplitude modulation, all of these things is not possible. Okay? You cannot do this for amplitude modulation, but angle modulation, you can do all these things. As an example, let's consider this message. Just the example in your book, okay, in your textbook. You see, you consider this message. Look at MT, right? This is our message MT. And let's say our message MT looks like this. You have all 0. Your message is 0. And then suddenly your message goes up linearly. It's a linear curve, right? Now, when you have this kind of message, let's see what happens when you do PM and FM. When your message is 0, your message signal is 0, then let's say we are going to do PM. So your message goes to the phase. But our message here is 0 anyway. So here's a 0, right? Because we are doing PM, but message is 0 anyway. So putting here as a 0. So you're going to get original carrier. So you're going to get just simple carrier. This is the same as your carrier frequency. What about the frequency modulation? Your message now goes to the frequency, but your message in here is 0 anyway. So again, putting 0 here, it's basically the same as your original carrier. So that's why whenever you have a 0 message, PM and FM, same, right? Both are same as a carrier because your message is nothing. Now let's start to increase your message in a linear way, like this. Okay, your MT message goes up linear. Now in this case, let's say in the linear curve, our slope is A, let's say. Right here is A equal to 1, but let's just say A. Then as we know, the linear equation, we can say like this, right? Maybe we can say T here. This is the curve. Because our linear here is slope is A, and this is a linear curve. It's like y equal to AT, right? And y is, in this case, maybe I can write it as MT. Let's call it this way. MT equal to AT. Is that right? Yeah, because our message is a linear curve, and slope is A, so MT equal to AT. Now put this MT into here, in the phase. And also put this MT into frequency. So that's the PM. In the PM signal, now you're going to put this message into the phase part. In the frequency modulation, now you want to put this message into the frequency part. Okay? This is your original FM signal. Okay. Now once you do that, let's look at the PM first. Okay. In this phase modulation, we're going to use this AT special message into here. Now then, we can write it as AC cosine like this, right? Like this. Because I put this AT into the message. This one, I can write it this way. maybe I can write it this way. So what I'm trying to say is eventually your message goes up linearly, then put this linear message into the phase part, and you can rewrite it here. Then eventually what's happening is your frequency is now changing. Earlier it was FC, but once you add this linear message into the phase and you combine them together, then you can see that now FC is going to change into this new frequency. We are talking about phase modulation right now, right? You're talking phase modulation. But once you add this kind of linear, increasing linear curve, linear message into here in the phase, eventually that happens like your frequency is now increasing into another frequency. That's what you're going to see. So that's why when you look at the output here, when the message was 0, it was this frequency. But once the message goes up linearly, now you're going to look at another frequency, right? And this frequency you see is a little bit higher frequency than this. And you see that the frequency is constant right here. And why is that? Because of this. This is a new frequency. Now your original frequency was FC. But now by adding the message, this linearly increasing message into the phase part, and you can rewrite it this way, then eventually it looks like the frequency is now changed, and now frequency is higher than before. So that's what you see here. Now then what happened when we use frequency modulation? Now put this linear curve message into here. Because we are talking about frequency modulation. Put this even here, then eventually when you do integration over this, you're going to get a 1 over t, a t squared, right? So what that means is your phase is going to be changing rapidly. It's like square, right? So that's why in this case your phase is changing much faster. So eventually it looks like your frequency is changing much higher. This is not constant. Here looks like a constant frequency, but this is not, right? The frequency looks like much faster. So that's what you can see from the frequency modulation. Let me ask you one question. This is one example, right? Let's think about another example. Not in here, but let's think about another example. Let's say our message is originally 0, but here suddenly it's like a staircase function. Suddenly goes up and constant. Let's think about such kind of message as another example. Okay, let's say it's like a unit step function, right? Unit step function goes and suddenly goes up and constant. If we have such kind of input message, what do you see in the phase modulation? Or let's say, what do you see in the frequency modulation? Let's say. That's maybe easier to look at. When you have a constant, but it's not 0, you have some value, but constant. In that case, what do you have? What happened is you have a one frequency, and suddenly here you change the frequency, but that new frequency looks same, right? Frequency is not going to change. Once it changes to a new frequency, that frequency stays. Okay? That's what you're going to have, right? You can see that here, actually. When you have some new value, in that case, MT is going to be constant. Right here, it's going to be constant. So put this constant here, and put this constant here, and you're going to get AT, not square, but just AT, for example. When you have AT here, then you can combine this AT here with this. Then you're going to come to another new frequency. That's exactly what happened we do here, right? You have AT here, and you're going to combine these two. Eventually, you're going to get new frequency. So the same thing happened here in the frequency modulation. But what if we put this message into here in the PM? You can do that here, same way. Then you're going to get this. Okay? You're going to get this. So what does that mean? You have original 2 pi fct plus some constant value. What that mean? What that mean is you have the same carrier, same frequency. Right? Frequency is the same. Suddenly here you have a phase shift, and then using the same frequency. That's what happened, right? Simply. Do you understand what I'm saying? You're going to have the same frequency here in the PM, but since you have a suddenly value suddenly changes, your phase is suddenly changed into some other phase, and then keep going with the same frequency. That's what what's going to happen. So important thing is you want to use this equation. Okay? How to do that is whenever you get a certain message MT, put this message M2 here and also your message into here. Then you're going to see what happened in the output by equations. Okay? This is a simple equation, right? You can calculate that. This next slide shows you a little bit of relationship between the PM and FM. Okay? The first picture here shows you that if we have a PM signal, how do you create FM? That's the first picture. You have a PM signal like this, right? Let's say you have a PM signal. Then based on this PM signal, put this PM signal here. Now you are doing integrator and multiply cosine here, then you're going to get FM. Okay? Because look at here, the PM, original PM and FM, the only difference is that in the FM you do integration. Instead, in the PM, you don't have integration, right? That's the only difference. So put this PM here, and then you do the integration, then eventually you can get FM. Same way, if you have FM signal, then from the FM you can get the PM. How do you do that? Doing differentiator. Since your FM is already integrated, you can do differentiating, then you can get the PM. So this one simply shows you the relationship between the PM and FM. Okay? Yeah. So that's some of the basic of FM, and we're going to continue the FM and angle modulation next time. Okay?